properly create this network. So we're turning the problem around. Given the network, we want to find the model for that network. So that's why we have the arrow going in the opposite direction. So with this affiliation graph model, so this is the graph, so we are given the graph G, set of vertices or nodes and the edges between them, and we want to find the affiliation graph model. So we want to find the model that will tell us which nodes belong to which communities given the network graph. So we have the affiliation graph M that's gonna show us which. So this is what we want to find. The affiliation graph that's gonna show us which node links to which node, the number of communities that we have, and what is the probability that two nodes link if they belong to the same community. So we are trying to estimate the matrix, the affiliation matrix that has the highest likelihood to generate the network for us. So we're trying to estimate the maximum likelihood. So that's called a maximum likelihood estimation. So given the data X, we can generate this data by some model. So F is the model, and these are the parameters of the model. So we want to estimate the maximum likelihood that affiliation matrix that's going to produce the particular network data for us. So what is the F? What is the probability of our model F with given parameters to generate the data for us? So we want to find the maximum likelihood matrix. And the way we will do this, so what this is showing is the maximum likelihood of probabilities that the two nodes will connect, and then we are subtracting out of that the probabilities that they will not connect. So there is a sum of all the communities they belong to and a sum of all the communities they do not belong to, and they are set the probability parameters. Now it is not very easy to do that, so we're gonna have to change our model a little bit in order to accomplish that. And what in particular we're going to change is, so far we had in the JSON matrix, we have a 0 if there is an edge between the two nodes, and a 1 if there is no edge between the two nodes, or the other way around. There is a 1 if there is an edge, and 0 if there is no edge. In any case, we either have a 0 or a 1. And so what we're going to change is, instead of 0 or 1, we will assign a parameter that is a number between 0 and 1 that tells how strongly this node is affiliated with that particular community. So we will give a coefficient of strength, how strongly that person belongs to the basketball community, or to the high school community, or to another community. And once we do that, we want to find the maximum likelihood that the numbers that we generated, which are these strength affiliations for each node, are going to generate the original network data for us. So we want to find the maximum likelihood. And the reason we're using log and not the bare probabilities is because if we're using the raw probabilities, we have to take a product of that. And if we take a product, then the errors start to add up. So instead of taking product, we take a summation. The log allows us to take a summation, and it doesn't change anything. So that's why it's called log likelihood. Okay, so next we will see how we're going to do this. So we are relaxing the model in a sense that instead of having a 0 and 1, for no edge and 1 for yes, edge or connection, we will assign a coefficient which is a number between 0 and 1 called the strength. With what strength does this node belong to this community? How likely is this person to be part of the basketball community? So the number will be bigger if they are strongly participating in the basketball activities, and number will be smaller if they are, said that they're friends on Facebook, but they don't really participate in these activities. So instead of having a 0 and 1, we will have a strength coefficients. So these are non-negative coefficients. This F. So this F is a coefficient that is showing the likelihood of the strength that the node U participates in the community A. So what we have here is U is the name of the node, A is the name of the community. Coefficient will be 1 if they are strongly affiliated, and it will be 0 if not affiliated, and it can be any other number in between 0 show the strength. And so, to show the likelihood for two nodes connecting, the nodes U and V connecting, what we're going to do is we will take the exponent raised to the power, the E raised to the power of those coefficients for both the nodes A and V. So we're taking a product. So this is 1 minus the exponent E raised to the power of product of membership strengths of the two nodes. So this is the probability that the two nodes are linked. U and V are linked if they belong to the community A. So this 1 minus the exponent of the strength coefficient of U and the strength for V. So it is the product of the membership strength of the two. And because it's a product, if both are members, then to a high degree, then the product will be large. So this big claim here is that from our affiliation graph model, we are moving to a claim that will allow us to detect communities in large networks. So I mentioned we are looking for the model that that allows us to find the affiliation matrix that is most likely to generate the graph for us. And we call that the in this case, since we created this strength, we're going to have a different matrix because the matrix before was showing us a 0 if there is an edge, if there's no edge, and a 1 if there's an edge. And now we're going to have the same thing, but instead of 0 and 1, the coefficients will show us the strength. So this is the strength matrix F, and the number here tells us these strength coefficients, the number in the matrix. So the row is for a particular, that's a vector for particular node. So vector for the node U, for example. Or this up here is the vector for the node U. The communities are here, so community A, B, C, D, and so on. And there's the row is a vector for the strength membership for this particular node in each of the communities. So the vector is showing all the nodes. The vector is showing all the communities the node belongs to. So what would be the probability that the node belongs to a particular community in that case? So look on that picture and let me know what you think is the probability that a node in the network belongs to a particular friendship community. Let's say that the community is that they're playing basketball together. I need you to please look on the screen. There's not time to do exercise now. We're gonna do that later. Okay? So just let me know what you think is the probability. So we're looking for the probability that the two nodes will connect if they belong to the same community. We have a big matrix. Imagine this is all the Facebook data, and it is placed in this matrix here. Each row shows one of you guys, one student, and then it shows all the communities they belong to. What is the likelihood you're going to be friends with another person is what this formula is showing. So what do you think is the likelihood? Well, we're just going to multiply the factors for each of the communities that you belong to and take exponent of that. That is the formula. That is for single community. So if two students are part of the same community, one community, then the likelihood is we will take exponent for the two nodes and their factors for that particular community. So that's going to be here, community A. If these guys belong to multiple communities, then we will take the product for the probabilities of all of the communities that they belong to. So this right here is C because C is for all of the communities.